Hello students, welcome to Standard 10 Subject Mathematics Chapter 10 Circles. This is lecture number 3. In this lecture we will see the number of tangents from a point on a circle. About the tangent, the definition we have seen, the tangent is a line which is passing through on one and only one point of the circle. So here we are going to discuss that on that circle how many tangents we can draw, and if the point is on the circle. So three situations we have shown here. In case 1, the point P is inside the circle, you can see, and we can draw so many lines through this point P. Now these three lines I have shown, you can draw many lines passing through P, but here you see that any of the line passing through P will be the tangent of circle. Let's see, this is not a tangent because it is intersecting the circle at two distinct points. This is also on P, two distinct points. This is also on two distinct points. So every line which is passing through the P point, which is inside the circle, no line is passing through only one point of the circle. They are intersecting the circle at two distinct points. So no tangent will be there. We will not find any tangent from inside the circle, the point. So therefore the case 1, the conclusion is there is no tangent to a circle passing through a point lying inside the circle, like this. If the point is inside the circle, we will get no tangent. No tangent will get. Now the case 2 is if the point is on the circle. Here the point P is on the circle here. On the circle. So you can see a line we can draw which is passing through this point, and it is tangent to the circle, intersecting the circle. So case 2 conclusion is there is one and only one tangent to a circle passing through a point lying on the circle. If a point lying on the circle, only one tangent you can draw through that point of the circle. Now next, third situation is the point P is outside the circle. Outside the circle. So how many tangents we can draw? One on this side, PT1 line, one tangent, and the other one is PT2. So two tangents we can draw from the outside of the point of the circle. So there are exactly two tangents to a circle passing through a point lying outside the circle. So this way, three cases we have seen about the number of tangents from a point on a circle. If the point is inside the circle, no tangent, zero tangents. If the point is on the circle, one and only one tangent. And if the point lying outside the circle, exactly two tangents we can get. So this is the very important about the circle and tangent, number of tangents, that we have to draw and write this and understand. Related this 1 mark question can be asked to us. Now after this understanding, we have theorem 10.2. Theorem 10.2 is the lengths of tangents drawn from an external point to a circle are equal. External point means this situation is given. If the point is an external, if the circle is given, and the point P is external, means outside the circle, we know that two tangents we can draw. Two tangents we can draw. So here also we have shown two tangents, PQ and PR in this case. Two tangents we have shown. So lengths of these two tangents are PQ and PR. They will be equal, that we want to prove. So this is the situation of this theorem. The length of tangents, that is PQ and PR, drawn from an external point, P, it is drawn to a circle, to this circle, are equal, that we know. So data is a circle with center O is given, a point P lying outside the circle, point P is outside of the circle, and two tangents PQ and PR on the circle from P. Two tangents you can see PQ and PR on the circle from P. To prove is the lengths of these tangents are equal. PQ equals to PR, we want to prove PQ equals to PR, this is only to prove. So proof is here, very simple proof is this. Let's join OP, OQ and OR first. we have to join this O to P, OQ and OR first. This is what we have to do. Join. Means this is the extra construction we have drawn, so we have shown it by broken line. Join OP, OQ and OR. Now, doing this, we have two triangles above OP and below OP. In that two triangles, we have to compare the equal things. In triangle OQP means upper side triangle, and triangle ORP, this is downside triangle. Two triangles we have. Just see which things are equal in that. So first of all, we can write angle OQP equals angle ORP equals 90 degree by theorem 10.1. Theorem 10.1 here we call. Theorem 10.1, you remember in that we were having, if a tangent is drawn, then the radius, if I draw from on the point of contact, it will be, the radius will be perpendicular on tangent, that we have proved in theorem 10.1. So in this case also you can see OQ is radius and PQ is tangent and Q is point of contact. So this radius OQ will be perpendicular on PQ, that means it will make 90 degree over here on Q. So angle OQP is 90 degree. Very similar to this triangle also. There is also OR in this side, the radius of the circle, and PR is the tangent and R is the point of contact. So radius will be perpendicular on tangent, that we know. So this R is also 90 degree perpendicular with this one. So angle OQP is equals to angle ORP because of 90 degree by theorem 10.1. Next, OP equals OP in both the triangles. OP is common. OP comes in this triangle also, OP comes in this triangle also. So common, that's why equal. Next, OQ equals to OR. OQ equals to OR because they are the radius of the same circle, radii of the same circle. So radii of the same circle will be always equal. Now showing this three things equal in these two triangles, what we have shown actually? One angle, right angle we have shown of that R. Right angles opposite side OP, that is hypotenuse in both the triangle is equal, that we have shown. And any one of the side, OQ is side of one of the side of this triangle OQP, and OR is also one of the side of this triangle ORP. One side are shown equal, OQ equal to OR. So this is right angle equal, hypotenuse are equal, and one side are equal. So RHS, right angle, hypotenuse and side. By that rule, RHS, these two triangles, triangle OQP, congruent triangle ORP because of RHS, right angle, hypotenuse and side. And as we know, if two triangles are congruent, their corresponding parts are congruent. So the second side of this PQ and second side of this PR will be equal. PQ equals to PR because of CPCT. CPCT means corresponding parts of congruent triangles. Second sides are corresponding sides. Corresponding parts of congruent triangle are equal. So PQ equals to PR. So this way the proof we have. That's the proof. So very simple theorem it is. This theorem is also very important. It can be asked in 3 or 4 marks in board exam. So very important theorem this is, and very simple also. So you are suggested to prepare this theorem, writing 2-3 times and prepare it well for the board exam. And this is the information also about the number of tangents from a point on a circle. This can also be asked on 1 mark. Any question can be made from this theory. So you write down this also very well in very well handwriting and prepare this. And this theorem is of 3 marks or 4 marks will be asked in board exam. So very important theorem and very simple theorem. You just prepare it. Thank you.